It's fabulous to see you all. You are all survivors, folks. This is amazing. Well done. So Philip, who I'm enormously proud of, asked me to talk about the 5 E's. And then today he told me it's gone up to 7. So, you know, that's what always happens. And I thought that the elegance of arches and domes might allow me to trespass across into my area of research, where arching is sometimes good, sometimes bad, and fortunately only very occasionally downright ugly. And this is the view at sunset from my college, St. Hilda's, where I'm now the principal and where I have absolutely no teaching or research role. So I think I ought to have the learner driver thing on me again. And it's such an honor and a great pleasure to join you here today. So huge thanks to Philip and the committee for doing that. So I'm just sort of see the dome here. This is the Radcliffe camera, which is essentially an axisymmetric rotation of an arc. And this picture is really quite an historic one. This was built in between 1737 and 1749 in the middle of Oxford. It boasts a dome that dominates the skyline, and it's the earliest example in England of a circular library. Where's Mariella? This is for you. Mariella works in libraries. Where are you, Mariella? There we go. She's not identifying herself. She's being very... There we go. Mariella, this one is for you. Okay? Important. She knows about libraries. And it was built in 3 stages externally and 2 stages internally. And this is a lantern dome in lead on timber, on an octagonal drum with a balustraded parapet with vases in plaster. You all wanted to know that, didn't you? And you all have to come to Oxford to see it. And it's a daily reminder in Oxford of elegance and efficiency in my view. Now, I am going to go back 2,000 years. And we find out that the Romans designed and constructed domes, they may have a hole in them, but that's all right, out of concrete. Much flatter than those covered with lead. And I think this is an example of the good. It's still accessible today, and it's innovative in multiple respects. Let's have a look at it. The most striking feature is the 27-foot or 8.23 meter wide oculus. It's self-contributing, and you all know this probably much better than me, to significant weight reduction. It's completely open to the elements, but that's okay in Rome. Weather's a bit better than at least at home in Oxford, maybe Zurich as well. And it functions as the building's only light source. But several other architectural innovations are to be seen. The coffered ceiling on the right. Now, how am I going to do this? Do I have to do this? There we go. Yeah, there we go. Oh, it works. Look at that. The coffered ceiling on the right reduces the weight of the dome. The mix of the concrete was already exceptionally light. They used, I think, sort of lava-type stone, which is much more porous. And apparently, also, they reduced the weight of the concrete as it went up the dome. And what I think is absolutely amazing, and may have been a bit more of luck, they actually managed to create a self-healing concrete as well. So well done, the Romans, I say, 2,000 years ago. So I'm now going to fast forward to what is ongoing good. And of course, this is elegant. I have to be a bit careful I'm not too nice to Philippe, because you know all about this. But he's done amazing work, but he was sort of building on what the Romans did 2,000 years ago. But still, he's reinvented and redefined some of these arches. I also was lucky to go and see the Isla exhibition as well, which also shows structures in a similar style. Very economic, very efficient use of resources, which pays back environmentally as well in reduced scope 1, 2, and 3 emissions during construction, and a whole host of other environmental benefits. And it was such a pleasure to be invited to come and visit your structures, Philippe, in the Biennale in Venice in 2016. And also we saw this very interesting, rather like the coffered roof. This similar example was also on display in Venice as well. And I really enjoyed the challenges of this era being taken up by combining sustainability with elegance and economy and efficiency, all of which hint to me at an ethical behavior to give the 5, now 7 E's as well, because of course education and teaching our students how to design in this way and the entrepreneurship associated with this are also very much part of it. So that's the nice bit about the structures, guys. I want to talk a bit now about the structure soil stricture. So I am a below ground person, right? And it's very easy to be elegant above ground. Arching in above ground structures is very convincing and it's often stunning, especially as I'm sure you've seen all the way through the conference. And I've only been here today, but I've been very impressed. It's been absolutely fabulous, so exciting. And as we've seen from the conference chair's chair, very impressive as well, Philippe. Well done. But I'm more interested in soil, mud pies and sandcastles per se, which is much more complicated, open brackets and interesting close brackets, but I'm on my own here, so I can't expect you to agree with me. And to achieve efficiency in economy of the structure above ground, we must also consider below ground the muddy, dirty, sandy, gravelly soil part. And it's the sort of, in German, it's the Hochbau against the Tiefbau. And sometimes arching is good in Tiefbau and sometimes it's bad. And I'm going to start off by talking a little bit about bridge abutments. So here we are. The second Severn crossing between England and Wales, England on the right and Wales on the left, is, I think, beautiful. It's efficient, it's economical, and the second one, which is this one here, the cable stay bridge, was built on time and to budget. This is not so common in my country, I have to say. Although being Swiss as well, I can also claim that, of course, it's always done here. And it's I think it's a very elegant cable stay structure. It was opened in 1996 and later named after the Prince of Wales. We have to have sort of a royal connection, don't we, somehow? And there were well-reported environmental considerations to do with plants and fish and birds, and these were sustainably managed as they were in those times. But how do you get on the bridge? It's only a work of art if you can't get onto the bridge. Laurent talked about that a little bit earlier on today, didn't he? And he mentioned the abutments. And I'm particularly interested because the design method on this abutment here used a design method that I developed in my doctorate at Cambridge many years ago. And there were deep peat deposits on the Welsh side. The Welsh is always a bit peaty and difficult, so there we go. That was excavated out and probably was not very environmentally good, but at least the structure was sound. And on the English side, they had these soft deposits, and it was necessary, quite deep, and it was necessary to build an embankment of between 10 and 15 meters to get onto the bridge. I mean, this is absolutely huge. And they did their sums, and they worked out that there should be 1.8 meter of settlements. That's my height at the moment now, I've shrunk. So huge amounts of settlements. And you imagine driving onto the bridge and suddenly having to jump 1.8 meters. That doesn't help very much, does it? So they had to find a way. They had to find a way around it. And so they built drains into the soft soil. And I'm going to show you what that looks like in a minute. And it was very important for me that my design method had been used in practice. I found it really helpful. This is just a very simple prototype structure. This was something that one of my doctoral students in Cambridge, Ed Ellis, looked at. And of course, when you have a soft soil over a stiff soil and you build piles, you put a pile cap on it, you build your bridge abutment, and of course the deck is going to be there somewhere later on, and you build up your embankment in time behind that bridge abutment, which causes a lot of excess pore pressure in this zone here and squeezing of the soil through the piles. Now, this excess pore pressure takes a long time to dissipate. So the best thing to do is to build in gravel drains that, even though they probably have all sorts of Scope 3 emissions associated with them, actually mean that you can speed up the construction. And I'll show you an example of that a little bit later on. And this meant that you could reduce the time of construction, so all of the costs associated with that could then be reduced. So that's sort of what was done in this particular case. And I'm now going to fast forward to about 2007, where a doctoral student from here did some work on those drains in our geotechnical centrifuge. And he built a prototype at 1/50th scale. And this was then, I can show you the next picture here actually, and where each of those drawing pins were placed, he drove in under the right stresses in the field. So this was a 1/50th scale model at 50 Gs, so the depth of the soil was about 8 meters, and he pushed in, and then he pulled out and pushed back in as sand was fed through a cable here into this tube. And you can see, again on the right here, after the test had been completed, what those sand piles eventually looked like. And it meant that the pore pressure, the water pressure, could dissipate radially, and the embankment was built out of lead shot to represent a 5-meter high soil embankment. You can see the bits of lead shot over on the right-hand side here, and this was it excavated afterwards. And the drains were 0.6 meter prototype diameter with a spacing of about 1.7 meters, representing an area ratio of what you might say 12.5%. And it worked really very well. And I just want to show you one set of results. This is from a 10% area ratio of improvement, in which we're plotting the settlement after the construction of the embankment against the time in years at prototype scale. So the time in the model is 2,500 times quicker, so 50 squared, and then in the field. It's a function of diffusion. I'm going to explain all the centrifuge scaling models now, but it was amazing. We could do in one day that test. So if you look at the top of the embankment and you don't have any drains, you're going to get 400 millimeters of settlement. If you put in drains, then that comes down to 250. And what's very interesting is you see the time where you're almost at 95% of consolidation, and that's 4 years in one and about 1 year in the other. So it can be done 4 times faster. That is hugely important for construction. And also you have a factor of settlement reduction of 1.6. So that worked quite well. And then you look at the toe here, and the settlement with drains is a bit quicker, but it sort of gets to the same place in the end. So the drains work really quite well. Yes, you have to have extra gravel, but it speeds it up, and that's quite positive. And you get arching also onto the stiffer inclusions, which are the gravel layers. But it's difficult to visualize that. So I want to now show you another good example, which is quite expensive because you're building concrete piles into the soft soil here, and you have a pile cap on the top, so that you can get kind of a 3-dimensional arch over onto those pile caps. This is called bridge approach support piling, and it's actually rarely used because it is so expensive. But this was work done by a bachelor student. It's lovely to see a bachelor student presenting this morning, by the way. Bachelor student from Cambridge who did this project and took lovely pictures of the arches underneath when he pulled away the base of his little box. And they developed a design method out of that, which is still used today. I think this is absolutely a beautiful example of how arching works really, really well in soils. And what you can imagine as well is that just under the arches here, if you've got settlement below on the soft soil here, you get a gap forming underneath the arch. And I'm going to come back to that later on for my ugly example. Now if we move on to what's sort of not so helpful, in a bridge abutment, standard pile bridge abutment, you have the lateral pressure on the piles that causes the abutment to move, or the pile cap to move this way. You have soil pressure in behind the retaining wall as well. And then you have arching forming onto this relatively rigid structure here. And this is important because when I first started my research, the Federal Highways Administration in the States wanted to know how much movement did there need to be at this point here to cause problems on the bridge deck. And all of that contributes to lateral movements at the bridge deck level. So now we're able to quantify the design for all of those three parts, so people actually know what's going on when they do it. This was Ed Ellis's work. Again, he's now teaches at Portsmouth University, and he captured it beautifully visually here and quantified it with some finite element analysis. And you can see from the colors there of the high stress in blue, of the horizontal stresses arching onto the abutment. And that was quite nice to be able to see that. But we can cope with the bad effects because we know how to design for it. Now, I'm going to come on to the ugly. Some of you may have heard, is there anybody here from the States? Oh, very good. Anybody here from Idaho? I want a sound, please, if you are. Yes? Somebody from Idaho? No? Nobody from Idaho. Well, that's just as well. This was where the Teton Dam was built. It was built over, I think, 3 years or so leading up to 1975. And it was designed to control flooding as well as provide hydropower and irrigation and drinking water. And it collapsed during the first filling of the reservoir in 1976, killing 11 people and, I'm afraid, 16,000 livestock. And it was due to a concatenation of fundamental design mistakes, ranging from failing to make the foundation impermeable, so their grouting curtain was useless, and the water leaked through, especially as you can see here on this right abutment. This is sort of modeling the rock across the valley. So let me just, that was the point that the failure occurred, and it had an arching over the valley. And differential settlement at this shoulder here between the deep layer of the soil and the shallow layer of the soil set up erosion starting at that point. And then also on top of that, they had a core dam with a really strange design, and they had, the shape of the core meant that the soil, as it settled, as you built it from the bottom up, it settled and it arched across onto the filters, and even worse, it arched across onto the core trench at the bottom. And what happens under an arch? I told you already, gaps happen. And if you happen to have water filling up on this side here, the water's going to flow through here, and it's going to have the same value of stress or pressure as the soil. And what happens then? It forms a quicksand, doesn't it, folks? And then you get piping and you get erosion. And because the silt was highly erodible, of course, that made it worse. And you got the thing called piping, and hydraulic fracture happened in the core. And it was an absolute disaster. I'm just going to show you quickly the pictures as the erosion occurred. It took 3 hours to empty the whole the dam. And it cost about 100 million to build. The federal government paid out 400 million in claims arising from the failure. The total damage estimates have ranged up to about 2 billion. And the dam wasn't built, even though the Federal Bureau of Reclamation, who were the sort of designer and owner, actually really failed to acknowledge fundamental mistakes. And it was not ethical. So that was a horrible example. And they wanted to just rebuild it as it was. There's many questions in a litigation-rich system about owning blame, and much to learn from other designers. So I was very lucky. Can you imagine being sent to work in Fiji? Guess who did that? Yours truly. So I was there in the 80s. I was very young, mid-20s. And what you can see from this picture here is, you can see the original level is in this dashed line at the top of the abutment. You see this very steep part here. So what did we do? We actually excavated it back to this line here, and when there was too much of a hole because the rock was weathered, we even filled it with concrete, which was pretty awful. But actually, it meant that the dam there wasn't any arching in this direction. And how do I know? Because I was responsible for quality control and all of these instruments that were installed along the way. And then the cross-section was interesting as well. You can see here that the core, it was a very plastic core. It was a very soft clay, the same weight of water as in soil, so it just deformed. And you can see the core is leaning on the under filters here. The water level's on this side, the under filters, and then this rock fill was lying on the top, so it forced it to deform, and arching didn't happen. And of course, I could tell that from the earth pressure cells that were built into it. So aren't I lucky to have had an amazing opportunity to be in charge of the monitoring and the reporting? And here's the dam. You can see it on the bottom right-hand side. I built dams on the beach as a 10-year-old. It motivated me as a young engineer. I really felt it was important to provide electricity to all of these communities through hydroelectric power. And for me, that was a really great opportunity. And the good news was it provided most of the electricity for a very long time, still almost half of that. Lots of Swiss firms were involved as well. And I just thought, as we move on to thinking about the environmental side, which SDGs could probably contribute towards that. And you can see a whole mixture of them, from not only providing power, safe and clean power, educating a workforce, providing decent work, all sorts of things. So I think this is really important. We used local clay, so the transport into the dam was the shortest it could ever properly be. We supported sustainable communities. We worried about the climate and all of this. So lots of things we could say were achieved with that. And I have to show you this picture, don't I? Who's that? This was me in my early royal connections, where instead of being called Springman, they called me Sandringham. And in my later career, I've been to Buckingham Palace, I've been to Windsor Castle, and they've given me gongs and things. I've never been to Sandringham, but maybe, who knows. Okay, I'm now going to become serious for my last few minutes. We are in an awful state at the moment. You've probably seen these pictures. This was when I came to ETH, 1997. Look what happened to the annual temperature deviations from the mean of 61 to 1990 in the various 10 years since that. It is horrendous. And you can look at it also in this sense as well, taking the same 1961 to 1990. This is horrendous. We have to do something about it. We cannot say that certain political parties are right and there is no climate change. Okay? It's really, really important. And so I'm very proud of ETH, actually. And I think ETH has done really a lot of things, and they have put their hands up to say, ahead of all other universities that I know at the moment, they want to get to net zero by 2030. And they've actually done their first Scope 3 emissions assessments in, I think it was 2017. So this was really, while I was Rector, actually. It's really, really good stuff. And so I just want to help us think a little bit in my last couple of minutes about what we can perhaps do. I think education is really important. And our own students in continuing education, and also the young in the schools. We formed an ETH Academy when I was Rector here. And this is a wonderful way to get through. So I think education is really important. I think research and technology, fusion, I gave as an example because I'm now in Oxford. Maybe that will work, maybe it won't, who knows. But there's blue sky research, there's applied research, and there's collaborative research and technology. This is just so important. And then I want to pick up on the other E, the last E, innovation, knowledge, transfer, and entrepreneurship. I'm a huge fan of this. And we've got some lovely examples from ETH, the Synhelion, sun to liquid technology to raise, to create energy. Climeworks, the carbon dioxide removal service, and there are many other systems engineering approaches. So I know all of you here are working in this area by saving resources. Please carry on and please shout about it. Please share with everybody what you're doing. And then I think the last thing we need to talk about are influencing policy and actions. And that can happen at all different levels. We have to worry about climate justice, human behavior, and there's all of the reducing all of the R's that we should think about. And then the compensation is a huge challenge. That's for somebody a bit more clever than a civil engineer to deal with, I have to say. I just want to give you two examples of what my college is doing to try and make a contribution as well. So we engage in ethical investments. I'm afraid it costs us money, but that's the way. And also just a nice example about biodiversity net gain. So we invest our endowment. It's currently 30 million in cash goes into this fund and 30 million in investment properties. And we have ESG, so environmental sustainability and governance, goals that we discuss with the Saracen Bank, which you all know from Switzerland, I'm sure. And we were a key initiator of this project. As I said, it doesn't make us as much money as if we invested in fossil fuels. But you know what? I think we need to be ethical, and that's important. And we also, my colleagues bought a 55-acre ancient woodland, and we do all sorts of wonderful things like genome satellites and eDNA measurements and all of the rest of it. And the students take photos, we go for walks, we do bioblitzes, all the rest of it. And these things are important to understand the biodiversity imprint of where you live and work. So I encourage you. I haven't heard of that happening actually at ETH yet, so maybe that's something colleagues can do. On that note, sunsets on structures represent all the 7 E's. Did you know, in passing, by the way, that the modern structural analysis of the Eiffel Tower, I've been told, as seen here during the recent Olympic Games, found that it would not be possible to save any steel anywhere on it, and that our Swiss Gustav had actually done an incredible and ingenious job all those years ago. Anyway, it reminds us we must always redefine, and we can still learn from the past. Thank you very much for your attention. Have a good rest of the conference. Thank you, Philip.